So my name is Mark Horowitz. I am not an after-dinner speaker like your previous speaker is. I actually am kind of a nerd, and I give kind of really technical talks, so I apologize ahead of time. I will say that the one tie-in I'll say to Tom's talk is that I've been studying technology for a long time. And I've been involved in, for people who know me, I've been involved in the IC business for over 30 years. And my comment about the IC business is that we're now in the age of cup holders. And I'm barely old enough to remember when cars were sold by how big the engine was and how many doors you had, because that really mattered. And then cars had enough of an engine and enough doors that people didn't care about that anymore. And you started buying cars because it had a really cool cup holder or electric windows or electric door locks, right? And so you were buying this very expensive piece of capital equipment because of relatively small features, okay? Roll forward 30 years or so, we are now in the age of electronic cup holders. We are going to buy devices because they have this cool widget, and I can talk to some other widget or something like that. And that's really what's going to end up selling products. And I think the driving, everything Tom says might be true, but the driving thing over here is we're going to have to convince you to buy a new thing, and we're going to convince you by giving you features you didn't have before, and that is going to take a little piece of silicon and probably a wireless communication device. And we can do that because us stupid people in this technology business decide we're going to spend millions of dollars, hundreds of millions of dollars to develop something and then sell it to you for $1. And so you can buy this amazing technology for relatively low cost. And as a result, we're already seeing things. Everything has a chip in it, right? My favorite example is the singing cards. We have really disposable technology. It's a fairly complicated chip. You open it once, you listen to the song, and you throw it out. Right? So the next thing is, with all the great technology and wireless that's happening, we're now going to have things that not only are really cheap and can compute, but they communicate. So it's the internet. Okay? But for those of us who have been around, saying that you have the internet and everything is kind of scary, right? Because it's actually worse than you probably imagine it to be. These are articles just from the past year about how the Internet of Things could kill you, hacking the fridge. Philips has this really cool lighting system called Hue, right, where you can remotely control your lights. Well, that means somebody who wants to break into your house can turn all your lights out before they break into your house, right? It's bad enough when people break into your computer and make it a zombie and they use it for nefarious things, but you don't notice. It's much worse when they break into your car or your sprinkler system and turn your sprinklers on or turn your house lights off or whatever. And there was actually a recent study, I didn't put it up here, from HP, where they just bought on the market 10 Internet of Things. 7 of the 10 had basically major security holes. I think it was over 50% of them did unencrypted updates. Okay? That means if you knew it, you could just download software that you did. Anyhow. So, as Tom said, you should, or Persis said, you should be a little worried. I'm a little worried. So, there are a group of people at Stanford, and actually some faculty from Berkeley and University of Michigan as well, who think that let's not repeat the internet, right? The internet was a good thing, but we now have all these security issues. Wouldn't it be wise to think about some of these issues a little bit ahead of time and try to build an architecture that's a little bit more secure? So we're standing up a new research program, hopefully with a 5-year horizon, where we hope to create essentially an underlying architecture of how to think about the Internet of Things that can give you security. And in order to do that, you have to think about systems, cryptography, applications, analytics, networks, a whole bunch of different things, all the way to human-computer interactions, because it turns out if you don't worry about the person, you'll build systems that are just broken in really obvious ways. And that's why it's a relatively large group of people. And what I'm going to do in this talk is just describe a little bit about what we're doing in these areas. And one of the things I want to say is that when we think about security, I think about security in terms of 2 basic ideas. There's data security, and this has to do with a lot about privacy. It's like the data that this system is collecting about me, how hard is it for someone to steal? And then there's this overall system security, which is how hard is it for someone to muck into that system and basically start messing with it. So you can have something where the data is very secure, but it's still relatively easy for people to get in and muck around. And that's one of the things that we're trying to get is because, as Tom said, it's a escalation war. So even if you build a secure system, it's likely someone will break in. You want it to be that when they break in, they still can't get too many things of value. OK, so I'm going to talk a little bit about the Internet of Things. I think of a slide. Tom already talked enough about it. I'm going to talk a little bit about why IoT security is hard. And then just to give you a flavor about the things that we're planning to do. Now, I can't tell you all the wonderful things we did, because we haven't done anything yet. I'm an honest guy, so I won't claim we've solved the problem yet. But I think we'll get, hopefully I'll give you enough of a reason to believe that there's hope. So the Internet of Things is a whole bunch of stuff. And unfortunately, as the hype increases, the breadth of what the Internet of Things is grows. So it is now going to be everything. It's not even the Internet of everything. It's just going to be everything. Because marketing says has to be that. But as Tom mentioned, one of the things that most people don't realize is that cars are very large electronic controls machines today. And they are going to be Internet in the near future. So they are going to be part of the Internet of Things. Obviously, there's a lot of sensors for fitness. And that's a big modern thing. There's a lot of home devices that are getting connected up. And of course, Nest, and then picture frames, and various other things that you probably think about already. Now, if you break down the Internet of Things, you could break it into various different areas. And I think one of the biggest areas today is industrial automation. And the problem, if you include everything in the Internet of Things, is that you won't be able to say anything about really the Internet of Things because the area is so broad. So I think it makes sense to think about this as kind of different application areas. There's industrial automation, there's home area networks, there's personal things that you wear, and then there's network devices in your home. And it turns out this industrial automation is a very different set. It actually already is a relatively large market, and it has a different set of problems. So we're not going to be really looking at that, but we are going to be looking at sort of the home, personal area, and network devices within your home. That's kind of the space that we're going to be looking at initially. And we're not initially going to be looking at autos or other things, because that's more on the industrial side. Now, and I attribute this, if I could remember who told me this, but it was some very wise person once told me when I was looking at CAD tools, is that if you want to build a tool to help you become more productive, the first thing you have to ask is, what is it going to prevent the user from doing? Because if you don't prevent the user from doing something, you can't possibly provide very much help, right? Because you only know within your tool something about some region, something specific. And so if we're going to try to improve the Internet of Things, we're going to have to restrict the space of what we're talking about. So we think about the Internet of Things as being an MGC architecture. Now, what the heck is an MGC architecture? Well, M stands for embedded, because I can't spell. It wasn't my abbreviation. Yeah. I'm part of a team here. I'm trying to go with the team. So most of the Internet of Things consists of a thing. So the thing is an embedded system. It usually has a small processor. It's energy restricted, a whole bunch of stuff. So these are parts of the M space. That typically communicates, because it has low energy, constrained wireless. It communicates to a local device, generally a gateway device, most often today a cell phone, but something, the beacon that the little device talks to. And of course, then that gateway goes to C, and the C is the cloud. Basically, it connects into the Internet into some kind of server space. Okay? And if you think about a large class of these Internet of Things, they are going to be a device connected to a gateway connected to the cloud. Now, you can argue with me that you don't need the gateway in all cases, whatever. I don't care. I'm going to build a system that has that, because that satisfies a large percentage of things. And if I keep that architecture constant, then I have some hope of basically providing automation tools. Okay, and then once the data is in the cloud, you obviously can access it by various kinds of user devices. Everybody with me? Okay, now one of the reasons that developing these systems is so hard and security is so hard is that you have to build the embedded thing in usually some C or embedded C, low-level programming language, and you're typically programming on ARMs or AVRs or maybe some TI MSP 430, some relatively simple processor. Then you go to the gateway device, and if you're an iPhone person, it's Objective-C going to Swift, and if you're a Google person, it's basically Java or JavaScript, right? And then the last part of the application you're trying to build is something that runs in the cloud, so you're building some web service backend. Okay, these are all different languages you have to have expertise in, and you have to have your application communicate across all that. It gets complicated. And because of that complexity, security is hard. You're dealing with a distributed system. You've got to deal with devices at different places. They have different languages, different OSs, different networks, very different computational resources between your teeny-weeny processors over here to Google in the cloud. There's many orders of magnitude different. Reasoning about the overall system is hard, especially when you're writing the detailed code at all the different levels. And then probably the biggest problem is, look, everybody wants to make money, right? So you don't make money by having security. You make money by developing the application. So what do you focus on when you're a startup and you're thinking about this? You focus on how do I deliver the service to the people? How do I develop this thing? And because security is hard, I'll worry about that later, right? And then you ship the part, and you kind of like it all works, and right? And then you get to the disaster I talked about in the first slide. Okay. So hopefully I've given you a little introduction to what introduction to things is, and talked about what the problem is. So what are we going to do about it? We have really two goals. The first goal is to try to think about cryptography or different ways of doing security that will make it sort of naturally safer to do the kind of computation we're trying to do. So one thing that would be great is, could you encrypt the data basically in the embedded device and leave it encrypted all the way up? Well, yeah, you can do that, but if you do that, you don't get any advantages of aggregation, because if you have encrypted data, you can't reason about encrypted data. So what are you going to do? So what is the trade-off there that you can do? And the second thing is, basically, can we solve Tom's second problem, which is the design complexity? Can we make it easier to construct these kinds of systems? And again, can we do that if we constrain the space into this particular class of IoT devices that we've been thinking about? Okay, so let me talk about each of those in a little bit more detail. I already said there are two kinds of security. There's data security and system security. So for data security, this basically limits what an attacker can do with your data. Unfortunately, it also limits what you can do with your data. Right? So there's a trade-off here, because the more capabilities that you can do with your data in aggregation, the less secure your data is going to be. Okay? And our goal and the way we're going to think about this is all in terms of end-to-end security. It doesn't matter that the gateway's secure, and it doesn't matter if the cloud's secure, if you can read the data through the pipe. As NSA has shown, if the data, or Target, right, showed, right, there, in the system that was initially hacked with all the credit cards, the data came in, the whole system dealt with it encrypted, but over here it was not encrypted. That's where they put the thing, and that's where they stole the credit cards. So how do you get the encoding as close to the device as possible, right? So that it's harder to steal the data along the way. So what is end-to-end security? It's pretty simple. It says the data gets originated in a device. It's in unencrypted form. You encrypt it. You deal with it on the gateway device encrypted. In the cloud, it's encrypted. And it only becomes decrypted on your personal device, so that nobody else, if they broke into those systems, could actually read your personal data. OK. But how can we possibly do that? How can we basically encrypt data and do any kind of useful aggregation on it? Because the whole reason we're building this Internet of Things is so we can learn things, and we can compare our water usage to other people in the neighborhood or whatever you want to do. So there's a really interesting invention that happened about 5 years ago called homomorphic encryption. So what is homomorphic encryption? It was the realization that I can take a sensor value, I can take a value S, and I can encrypt it to be SE. something else. But unlike most encryption, it's actually possible to do computation on SE. So I can take two SEs and I can add them together. I can multiply them, whatever else. I don't know what they are, but I could do an operation on them. And then you can give me that operation and the result back. And I can then decrypt it and tell you what that product was, even though you who did that multiplication don't know what the numbers are. Okay? It's pretty amazing. Okay? Now they proved you can do this in general. The problem is it's about 1 million to 1 billion times slower than doing it normally. Okay. Really interesting if you're a theorist, not so interesting if you're trying to build an Internet of Things thing. Right? But it turns out that for specific computations, there are ways of doing the encryption that if you only needed to do addition or linear operators, you can do this and it's not that much slower. Okay? Oh. So what we're going to try to do is we're going to explore what kind of encryption we can do, what's the computational overhead of doing operations with that kind of encryption, and is there some nice boundary that I can do enough analytics to satisfy what I need without revealing what the values are. Okay? And this is a research problem that we're working on. So the faculty member that's working on this is Dan Bonnet, who's a cryptography expert, and Chris Ray, who's a data analytics expert. So these are two faculty members of the CS department. Right? And we're going to try to figure out, is it possible for devices to compute in aggregate without revealing their own data? And the results so far are promising, right? But we don't have the right encryption scheme yet. And that's what we're going to look at. And we're going to try to look at what the trade-off curve is, how much analytics you need to do to be able to get this done. The second goal that we're trying to do is to implement this framework that makes it easier to build the Internet of Things. And it turns out that when you build an application, even though the application has sensor data, gateway data, server data, the kinds of operations that you're usually dealing with is you're collecting some data, and then you're transforming that data in some way. Basically, you're averaging it, or you're doing some different view of that data, and then you're going to present it as a graph or a chart or whatever you want. And so we're going to build a language that lets you describe what data you want to collect, what operations you're going to do on that data, and how do you want to present it, independent of where it's being done in this space. Okay? And then what we're going to do is basically allow you to, or have that tool partition it in different places to figure out what's the most efficient for your application. And so Phil Levis has already built a prototype system called Drell for doing this, and David Marizieras, these are also both faculty in the CS department, are looking at how to actually build the system and deploy it. Okay. So of course, it's the Internet of Things, so you have to worry about the networking aspects. And so we have people working about protocols, how to do some of the different link layers, how to make it very energy efficient. How do you deal with the fact that the wireless is a really crappy link layer? Right? If you're trying to get data across, it's very unreliable. So we, again, have a couple of faculty members, Keith Weinstein and Prabal Dutta. Keith is at Stanford, Prabal is at the University of Michigan, who are working in those areas. And then the area that I'm personally most interested in is this thing called software-defined hardware. My shtick is that we have this amazing hardware. Technology today can do almost anything. The problem is the people who know how to use the technology are not the people who know what applications to solve. Right? Those people tend not to be the technology experts. And we need to better enable people to create hardware or to leverage the hardware that's available. And so we're doing a project called software-defined hardware, which basically says from this description that people are writing, can I actually look up in a library, give them the build the materials, and have them basically play around with those materials to get the form factor they need for their embedded device. So we can automatically generate the embedded device for them, so they don't have to be a hardware expert to do that. And there's lots of interesting questions there, because if you automatically generate a device for somebody, anybody who's built hardware knows that when it first comes back, it never works, right? I've never built a system. I mean, even the systems that I built, my chips always work for silicon. But they never work the first time I turn them on. And so you have to work on how you're going to debug these systems that are being generated that way. And the last thing I want to say is, look, if we're going to build the system, the last thing we have to do is we have to make it easy to use. Because, as we all know, it doesn't matter what kind of security you put in the system. If it's too hard to operate, people will just defeat it in very clever ways. And so we have people on the human-computer interaction side to make sure that the things that we put in are going to basically be used, because otherwise it's all for naught. OK, and with that, I'd like to thank you for your attention.